Hello. We're starting the final part of our class. We're going to be talking about cosmology, which is the study of the universe or the cosmos as a whole. Now, I know this sounds very much like cosmetology, but it's not. But actually, cosmology and cosmetology are very similar in one way. Cosmos means order. And with the universe, we're studying like the order of the universe. With cosmetology, you kind of want order too. So the root word order, cosmo, is the same. So actually, it would be very interesting if you're not sure of a major yet. If you have a combined major of cosmology and cosmetology, I think that would be very, very interesting. I'd give you an extra point if you decide to major in both cosmology and cosmetology, because that would be very cool. Well, all right, the study of the universe or the cosmos as a whole. Now, I remember we went to a SETICon, search for extraterrestrial intelligence, some years ago. I went with Joe and some other assistants, and Joe went to a lecture where he heard Alex Filipenko, who's at Berkeley, give a talk about cosmology, and what Joe heard him say is the only difference between cosmology and cosmetology is ET. Now look, see the ET, right, in cosmetology? So Joe added this slide in. It's one of Joe's better things he's ever done. It's a good slide. All right. Now this is good to write down. What we know today about the universe as a whole, so that's cosmology, the study of the universe as a whole. What we know today about that, or the universe as a whole, began with the work of the same person that discovered that other galaxies existed, Edwin Hubble. So Edwin Hubble, who's the one that, with the work from Henrietta Leavitt, discovered that other galaxies existed, well, with Hubble, that is known as the father of modern cosmology. And we'll talk about why he's known as that. What we know about the universe today, which is pretty profound, started with Edwin Hubble. Now, remember Hubble was working at Mount Wilson in Los Angeles in the early 20s, and that's when he used the work of Henrietta Leavitt, her period luminosity relation for Cepheids, and he was able to figure out, based on her work, that this Andromeda Nebula that he took pictures of and everybody thought was this spiral nebula within our galaxy turned out to be another galaxy. So the Andromeda Nebula was actually the Andromeda Galaxy. And after that, he figured out there were billions of other galaxies out there. So the universe went from being one galaxy, the Milky Way, to, in the course of one night, billions of galaxies, which is amazing. So this happened pretty much in one night in 1924, and that's what Hubble was first became famous for. Well, what happened was this. Somebody else to write down besides Hubble, and it's good to know these people. On the probably the final, I'm going to be putting some of these names here, probably not on the last exam 4, but on the final, it's good to know these people. Milton Humason, who was actually Hubble's assistant. He didn't start off as Hubble's assistant. He started off as the mule team driver who carted up the equipment to make the telescope on Mount Wilson, where Hubble was studying. And so he was like carrying all this equipment up and became very interested in what Hubble was doing and kind of hung around a little bit. And eventually Hubble hired him to do work because, you know what, Hubble had a lot of work to do. After you discover one galaxy exists or another galaxy besides the Milky Way, well, then if there are billions of other galaxies out there and you want to measure the distances to them, well, you can't do billions, but I mean, hundreds of thousands of galaxies maybe you want to measure the distance to. Well, you don't want to do all that work yourself, so what do? You hire an assistant. And Humason, after a while, became such a good astronomer and pretty well-known astronomer. You know what he did? He hired an assistant. So that's kind of how the way things work. So Humason was Hubble's assistant that helped him out in a lot of collecting a lot of data. Now, what Hubble and Humason discovered about galaxies. Take a look at this. Now, you don't have to write this down yet. I have something for you to write down. But they figured out when they got the redshift or the spectrum of a galaxy, they figured out almost all of them had a redshift in their spectra. Now, we talked about stars having a redshift. Remember the redshift or blue shift? What does a redshift mean that we talked about? Remember a Doppler shift, a redshift? Doesn't that mean this? If almost all galaxies exhibited a redshift in their spectra, it meant that almost all galaxies were moving away from us. So almost all galaxies are moving away from us. It's kind of weird. Well, so that's kind of good to know. I mean, what's in red here? They figured out that almost all galaxies are moving away from us. You can write that down. Now, they went on and further figured out something. Well, first, let me show you this. A spectrum. Spectrum, a dark line spectrum of the sun, a dark line spectrum of a supercluster of galaxies. Now, notice this. Notice the dark lines. The same dark lines are there, but notice they don't line up with these ones. Look at these. This pattern there is shifted this way. This line is shifted that way. So you see that they are shifted in the cluster of supercluster of galaxies. They're shifted towards the red, a red shift. So if you see the dark lines shifted towards the red, it means galaxies moving away. And this supercluster of galaxies, this whole supercluster of galaxies is moving away. Now, here's something else they discovered. The farther the galaxy was from us, and they were able to get the distances of galaxies by using Cepheid variable stars from like with Leavitt's work, period luminosity relations. So they were able to get the distance of the galaxy, and they found out that the greater its redshift if the galaxy was farther away. So the farther the galaxy from us, the greater its redshift. You remember what redshift meant? Moving away. So you know what this means? The farther the galaxy from us, the faster it is moving away from us. Because remember, a bigger redshift, bigger Doppler shift, means moving away faster. So the farther the galaxy, the faster it is moving away from us. That's good to write down, because that is called the Hubble law. The Hubble law states that the farther the galaxy, the faster it is moving away from us. Now, not all galaxies are moving away from us. I mean, galaxies like the Andromeda galaxy is galaxies in a local group, relatively closer ones. Some of them had blue shifts. Some of them were moving towards us. But on a large scale, if you go farther than the local group, which pretty much everything is, all these galaxies, the farther the galaxy, the faster it was moving away from us. So this is kind of weird. I mean, there's something wrong with us. Why are they moving away from us? And their farther galaxy are moving away from us faster? Well, this is an animation, but it's not going to work here. What it's showing, what it would have shown, is that if there were a closer galaxy, here's distance, that, and this represents a picture of a closer galaxy, the dark lines, let's say two dark lines you're looking at are here. If there were a farther galaxy, you see this galaxy farther, a galaxy farther in the distance, the dark lines would be shifted, same dark lines would be shifted more to the red. And if there were even farther galaxy, more to the red. And even farther galaxy, more to the red. So the farther the galaxy, the greater the redshift of the dark lines, which means the faster it's moving away from us. So that's the Hubble law in graph form. Maybe this is a little better. You don't have to write this down. But showing you, if a galaxy is farther away, its velocity of recession, radial velocity, is faster. The farther the galaxy, the faster it's moving away from us. Again, it's the Hubble law. Now, this might be a good thing to write down. It's called the Hubble constant, or H. It is the rate, approximate rate, at which galaxies are moving away from us. It is about 70 kilometers per second for every, MPC? That means megaparsec, million parsecs. So for every million parsecs, a galaxy is away from us. Remember, parsec is about 3.26 light years, so a megaparsec is about 3.26 million light years. For every megaparsec, a galaxy is from us. It's moving away at 70 kilometers per second away from us. It's like from Santa Rosa to Marin in 1 second. But if there were a galaxy 2 megaparsecs away from us, it's moving at about 140 kilometers per second. And if there were 3 megaparsecs, 210 kilometers per second. Now, you really don't have to do anything with this number. I'd like you to know this number, the Hubble constant. So it's showing you a farther galaxy is moving away from us faster. Now, you know what this means? The universe appears to be expanding. But when we say the universe is expanding, what is expanding? Are galaxies moving away from us in reality? Are galaxies moving through space away from us? We don't think that's the case. This is a little bit weird. What they say is this: the thing that's actually expanding is space-time. Space-time is actually expanding. So that's kind of weird. You say, what the heck? How is space expanding? Well, remember we talked about general relativity, where space-time could be warped, could be bent? Well, if it could be warped and bent, why couldn't it be stretched also? So we think that galaxies are not moving through space. It's the space and time between the galaxies is getting stretched. You may say, well, what's the difference? Well, let me show you what the difference is. First, I wish I could show you this with a real video or a real demonstration in class, but here's what you have to do. Think of coins glued onto a balloon, coins that represent galaxies. Well, if you blow up the balloon, don't the coins get farther apart? Yeah, they do. And the ones that are farther, coins that are farther apart actually move even faster, appear to. And it's not because the coins are moving along the balloon. What is it moving? What's expanding? It's the balloon that's stretching. The balloon that's stretching, but the galaxies don't appear to be really getting bigger at all. That's the way it is in real life. Galaxies don't appear to be expanding or getting getting stretched. The space between the galaxies is getting stretched, and the more the space, the more the stretch. Now, this analogy kind of works, and this is kind of neat because you know what it shows? It shows where the universe is expanding. It's not expanding into a direction you could point. It's expanding into another dimension of space. You cannot point to the direction at which the universe is expanding. It's no direction you know. It's no direction anybody knows. If this represents, the surface of a balloon represents all the dimensions in the universe, it's a direction outward. Just like the direction inward is where mass warps space and time. Well, the universe is expanding outward in this view, but you cannot point to that outward. The only way you can point to an outward here is because you've shrunk the universe into like a two-dimensional fabric. But if we had three dimensions of the universe and one of time expanding, it's expanding into a fifth spatial dimension. You cannot point to the direction that the universe is expanding. Well, this analogy, I don't know, it kind of works. I wish I could draw this for you. But think about this. I know this is supposed to be raisin bread. Imagine raisins and raisin bread. And they're, let's say, a Milky Way raisin, and I don't know, and another raisin here, and even a raisin that's maybe even farther away. Well, let's say that's the Milky Way. Let's say there's a raisin here that's 1 inch away, and a raisin here that's 2 inches away from us. Well, if the bread doubles in size, doesn't that mean that the raisin that was 1 inch away is now 2 inches away? So it went 1 inch, let's say, in an hour. But the one that's 2 inches away, if that doubled, it went to 4. So that went 2 inches per hour. So do you see that galaxies and space-time are not moving through space-time? It's the space-time expanding just like the raisin bread's expanding. These raisins are not tunneling through the raisin bread. If that happens, if you make raisin bread and the raisins have tunneled through it, do not eat that raisin bread. There was something going on. So think about raisins and raisin bread. And this is one case where the picture I would draw on the board or the screen is better than this. I don't even know where I got this. I need to get rid of it. But think of raisin bread. If you think of space-time expand, then at least you have three dimensions, right? Three dimensions expanding into it'd still be expanding into another dimension you didn't know, but at least it's a little more accurate than the coins on a balloon. Now, let's talk about this. You might recognize this guy. Well, Einstein. Here's an Albert Einstein right here. Now, before it was known that the universe was expanding, it was thought, and after we knew that other galaxies were out there, Einstein knew about something. He knew about the warping of space-time. Well, he came up with it. That's general relativity. Well, he felt this. He felt that the universe has always been the same. It is infinitely old. And he knew if galaxies are just sitting out there, which they thought they were at the time, that's almost impossible. Over time, galaxies should have fallen in on one another because of gravity or the warping of space and time. Well, what Einstein did to satisfy his need to have a universe that he kind of thought it was, he came up with something called the cosmological constant. That's good to write down. What was this? It was an anti-gravity force that kept the galaxies from falling in on each other. Because the galaxies, I mean, the universe is infinitely old, and the galaxies are just sitting out there, and a long time ago, they should have fallen in on each other. Well, they should have already been fallen in on each other. There's only one way to explain that they're just sitting out there. There must be an anti-gravity force, and he called it the cosmological constant. Now, later on, when Hubble discovered the universe was expanding, and the galaxies weren't just sitting out there, they were actually moving away from us for the most part, Einstein said when he came that this was the biggest blunder of his career, to come up with this, to just with no experimental evidence at all, that this anti-gravity force existed. He just thought, it must be there if the universe that he thought it was. Well, it turned out it wasn't the universe he thought it was. It was an expanding universe. He didn't think that at the time. And he said, oh, man, I shouldn't have done that. Shouldn't have come up with it. But, hey, if Einstein makes a mistake, then don't feel so bad when you make a mistake. All right, now, let's talk about someone else here. I'm going to talk about someone named Georges Lemaitre. You can see him at the bottom here. And Georges Lemaitre, let me tell you about his idea. I'll show you a little bit more of him. Well, I'm not going to show you too much of him yet. You can see the top of him right here. He was a Belgian priest. You write down Georges Lemaitre. Now, what he said was this. This is pretty profound. He said, hey, if the universe is expanding, and he even had an idea that the universe might be expanding even before Hubble figured out it was expanding. He said, doesn't that mean that, well, that galaxies, if they're moving away from us, and each day they get a little farther from us, doesn't that mean if you go back in time, let's say you go back a few years, everything would have been closer together? And if you go back maybe hundreds of years, they should have been even closer together. And if you go back millions, maybe even billions of years, everything should have been together. And then something happened when everything was together, whatever this everything was. Something energetic happened to start this expansion of the universe. What is this the idea of? Yep. It is the idea of the Big Bang. A Belgian priest, I think it's pretty cool, named Georges Lemaitre, came up with the idea of the Big Bang. Now, he didn't call it the Big Bang. He called it the primeval atom. But it's the same thing as the Big Bang. Actually, it was called the Big Bang by someone who didn't like the idea, to ridicule it, that we're going to talk about in just a minute here. So Georges Lemaitre is the one who came up with the idea that the universe began in what is known as the Big Bang. That's good to know. But at the time, this was not even, wasn't even a theory. I mean, there was no evidence for it whatsoever. It was maybe a hypothesis, you can call it. But a lot of people did not like this. Well, one person in particular was Fred Hoyle. Should write him down. Don't worry about the dates, though. Fred Hoyle said, no, the universe didn't begin. It has no beginning or end. Now, Einstein kind of felt this way at the beginning, but when he got evidence, Einstein was a pretty good scientist. He said, hey, the universe seems to be expanding. My idea is not correct. Well, Hoyle actually was a pretty good astronomer and a pretty good scientist, but things are a little screwy. He said the universe has no beginning or end, is infinitely old, always looks the same, and this is called the steady state theory. The steady state theory. Now, the steady state theory is that the universe did not begin. It's always been the same as it looks now. And people had a problem with this, though. Some people had a problem with this because they said, hey, Hoyle, the universe is it's expanding. And if the universe is expanding and galaxies are getting farther apart, how does it always look the same? Well, Hoyle said, well, here's how it does. That when galaxies get farther apart, and if you wait long enough, according to people, you wouldn't even see galaxies whatsoever for the most part. Hoyle said that what happens is that between galaxies is that matter springs out of the universe, out of existence, called continuous creation. And galaxies are created between galaxies to make the universe always look the same. And people, as other scientists said to him, hey, this sounds a little weird, how this, just the creation of matter from nothing. He couldn't explain that. But you know what? Hoyle was the guy that came up with some monumental ideas. Before Hoyle, people thought that all the elements were there from the beginning of time, all the heavy elements, iron and all these heavy elements, that that we know today that stars create when they die. Well, guess who came up with that idea? It was Hoyle. It was the idea of nucleosynthesis. You should read that chapter in the tidbits. Hoyle said it's stars that create the heaviest elements. And they, especially when stars are dying, and that's why the universe has not just hydrogen and helium, but heavier elements now. And now, I mean, that's monumental. That actually we believe, and that we know that to be correct right now. And that was Hoyle. So Hoyle had some great ideas and things that came out, were correct. But this one, the steady state, there was some people who did not really want to go for this. However, they didn't really want to go for Lemaitre's idea either, because this is kind of unfair. They said, hey, this is a priest that's coming up with this idea in physics. And even though Lemaitre was an incredible physicist, and I mean, great mathematician, people thought that, hey, if he's a priest, he's not going to be able to do some science, figure out some scientific principle or be that great at science. But that's a pretty biased way of thinking. Now, he was a priest, but there are a lot of priests who are also scientists. So even today. So I think that was a little unfair. So the scientists a lot of scientists didn't want to accept him just because he was a priest and what he said. Now, Hoyle's idea was a little strange of this continuous creation, but you know what? Hoyle had a radio show, and Hoyle would go out and broadcast different things, ideas, and people were listening to him. You know how if you listen to someone for long enough, even if you may not agree with what they say, you might say over time, hey, this person, I hear him every day, this person must know what they're talking about. Well, that's that's a fallacy there. With an appeal to authority, or I don't know if that's what that is, but it maybe not. My critical thinking class is a long time ago, even though I loved that class. But but Hoyle, since he went out and he marketed his idea and talked to people, I mean, I'm not going to compare him to someone like Rush Limbaugh, but you know how Rush Limbaugh, if you hear someone like Rush Limbaugh, I mean, maybe it doesn't work for me, but I can imagine that there are certain people that listen to Rush Limbaugh enough, and they might go for some of his ideas. Even they wouldn't necessarily listen, go for him before, but if they listen to him enough. Hey, hell, you guys have listened to me for a long time, and you try to trust the stuff I say. You see what happens when you listen to someone for long enough? You start believing them. Well, I try to tell you the truth. I'm wrong sometimes. All right, I'll keep moving on. This is starting to sound bad. All right, so now, which one of these guys is correct? Is the steady state theory right? Is the steady state hypothesis, they should have called it, is the Big Bang idea correct? And it's actually Hoyle who didn't like Lemaitre and I don't think he liked Lemaitre, to tell you the truth, because he didn't like Lemaitre's idea. And he said one time, yeah, you're going to listen to Lemaitre and his Big Bang idea? Well, that was he tried to ridicule the primeval atom. So it was actually Hoyle who called Lemaitre's idea the Big Bang as an insult. Well, let's move on a little bit here. George Gamow. I know it looks like Gamow, but he's a Russian astrophysicist. He said this. He said, he felt that Lemaitre was correct and that Hoyle was wrong. He felt that the Big Bang made sense that it happened, and that Hoyle's steady state didn't make any sense to him. And he would actually go to lectures with Hoyle being there and ask Hoyle questions that Hoyle couldn't answer, and they did not like each other. And but it turns out, so what Gamow said is that, okay, I think there's a Big Bang. If there were a Big Bang, some energy should be left over. If we can figure out this energy, discover this energy, well, maybe we can have evidence that this Big Bang did happen, this beginning of the universe. But at the time, there's no way to discover this energy. There was just a prediction, mathematics. Now, Ralph Alpher, he was actually Gamow's student. He was one of the guys. He was more of a fighter for Gamow's ideas than Gamow himself. So it's good to know Ralph Alpher. And he was a big proponent of course, his teacher, Gamow, and also Lemaitre. He did not, really like Hoyle and his ideas. So good to know Alpher was Gamow's student. Now, let's talk about going all the way to 1965. At the time, the two competing hypotheses were the Big Bang and the steady state. And neither one was really a theory, even though they still call steady state a theory, but not now. But let's see what happened then. These two, well, they're physicists. They're not astronomers. Penzias and Wilson, Arno Penzias and Robert Wilson. They were Bell Lab technicians. You know Bell Lab, like Pacific Bell Telephone Company. They were working in Holmdel, New Jersey. And they were working on this thing that was called a radio horn, radio microwave-like receiver. And from this receiver, what they were getting is this static coming from space, every direction, all over, as if space was a little bit warm by about 3 Kelvin, which is about 5 degrees above absolute zero, 5 degrees Fahrenheit. So 3 Kelvin is meaning space is a little bit warm, as if there's like microwaves. There are microwaves coming from space, as if space was kind of like a big microwave oven, and energy coming from pretty much everywhere. Now, they didn't understand this. They felt that maybe it was some other phenomena. There must be something else wrong with this telescope, because they were just looking for satellites. They were looking at the telephone satellites. They were trying to get signals from telephone satellites. They were not doing any astronomy, not trying to do astronomy. Well, they went into the telescope at one point, into this horn, and found pigeons living there. Well, if there are pigeons, do you know what pigeons leave? You know what pigeons leave. They don't leave, well, they leave pigeon droppings. So what happened was they had someone go in here, clean up the droppings, and then take the pigeons away. But they were homing pigeons, and the pigeons came back and were causing the same problem. So someone went in there. It wasn't Penzias and Wilson. You know, it's one of the, I guess, maintenance people went in there and permanently got rid of the pigeons. Don't ask me. I don't want to talk about that. I don't even know how. I decided not to even look into it further. But the pigeons were gone. But even after there were no pigeons and no pigeon droppings, they were still getting the signal. So it wasn't the pigeon droppings that were causing the problem. They thought, oh, maybe it's an airport. Maybe it's a nearby airport getting signals from it. They ruled that out. But what happened was this. They heard they heard at a nearby university, Princeton, which is also in New Jersey. There was an astronomer by the name of Robert Dickey, and this astronomer was using this kind of telescope I called it a Dickey radiometer, to try to pick up the energy left over from the Big Bang that Gamow had predicted. This energy that would have been about 3 kelvins as the space is slightly warmer. And Penzias and Wilson read about what Dickey was doing and said, my God, could this be what we found? So they got in touch with Dickey, and so they collaborated together, and guess what? This energy that Penzias and Wilson that they discovered was exactly what was predicted by Gamow. If there had been a Big Bang and the universe had cooled down to the point where there are just microwaves coming from all directions. So what they discovered is this cosmic background radiation, Penzias and Wilson. Now, let me show you this. I decided to go here, and I'll have you write down something in a minute. One time I went to New York to visit my cousin, in New Jersey, and I had relatives in New York. And my cousin in New Jersey, I said, hey, you know what? I can write off this trip on my taxes. If I go to this, I've never been here. I mean, I grew up going to New York to see my relatives. Let's go here. And my cousin said, yeah, it's only 25 minutes from here. I've never been there either. So we drove up to this microwave horn, still in great shape. This was probably about 10 years ago or so. And you can just drive up here. No one's even around. I mean, it's just like abandoned. And it looks like it's in great shape. And there it is, this microwave antenna. And here it is. Look at this, the horn antenna. This is a national historical landmark. And this is just, it's a piece of history now. And look on this plaque. It says, with this large horn antenna, Arno Penzias and Robert Wilson discovered the cosmic background radiation in 1964. It was verified in 1965. This unexpected discovery, the first evidence that the universe began with the Big Bang, ushered in experimental cosmology. So after this was discovered, energy that was predicted, if there was a Big Bang, this microwave background radiation, well, the steady state theory went out the window, and Hoyle's idea was scrapped for that. And this now is called, what we call this energy they found, and it's really not 3 kelvins, it's like 2.735, but we call it 3 kelvins. It's called the 3 Kelvin microwave background radiation. It is evidence for the Big Bang. Doesn't prove anything. In science, again, you don't have proof. You just have evidence. You have enough evidence. You go on that. And so this is evidence that the Big Bang happened. Now, Hoyle, even after hearing about this, he refused to accept this. He refused to accept this evidence for the Big Bang. Now, Hoyle was a great scientist, but if you're a scientist and you're presented with evidence and you refuse to accept that and keep going with your own ideas if they're not even supported, that's not being a good scientist. You have to be ready to let go of your cherished ideas when you see that they're not correct. That's what makes a good scientist. You can't hold on to things just because you want to. Well, Penzias and Wilson, you don't have to know this, but they won a Nobel Prize in Physics in 1978 for the discovery. And this discovery was made by accident. Oh, this is, yeah, it's like one of your assistants, like John or Joe, coming to school and, stepping out of their car and stepping on a rock. And they look at this rock and look kind of weird, picking up the rock. That doesn't look like an Earth rock. Taking it into a lab, finding out it doesn't seem to be an Earth rock, and they test it a little further and find out this rock somehow came from the planet Mercury. It's something that was blasted off of Mercury, and we have actually a piece of Mercury on the Earth. And Joe or John, win a Nobel Prize in Physics for their discovery because they happened to step out of their car and step onto a rock. Now, I'm not saying Penzias and Wilson didn't do anything. Of course, they put two and two together, but it still was an accident what they found. And I am not comparing Penzias and Wilson to Joe and John. That would be kind of an insult to Penzias and Wilson. So don't take it that way. So I didn't mean to offend them. So and a Nobel Prize in Physics in 1978 was like $400,000. Yeah, if you get a Nobel Prize these days, it's something like, I don't know, $1.5 million. So it's a good little bonus to your salary. Now, don't want to show that. They're going to skip here. I want to skip to this. The Wilkinson microwave. Actually, you know what? I'm going to pause this now. I've been talking too long here. We're going to start this up for the next class, and we'll start with this spacecraft. And we will talk about some further evidence for the Big Bang. So that is it for now. And stay tuned for Cosmology Part